Welcome back to linear algebra. In this video, I want to talk a little bit about LU factorization. The idea of factorization is something that you have seen many times throughout your mathematics career. In arithmetic, we learn how to factor numbers. 72 we might recognize is 9 times 8, and of course 9 we know is 3 times 3. 8 is 4 times 2, and 4 is 2 times 2. So we can find the prime factorization of a whole number. When you go on to algebra, you learn how to deal with things like x squared plus 5x plus 6. And you realize that you can factor this polynomial as something like x plus 2 times x plus 3, right? Oops, not negative 3, x plus 3, right? Two numbers that multiply to 6 and add to 5 are 2 and 3. And you use that to take a polynomial equation and turn it into a system of linear equations. Or you could use that or the prime factorization if you're dealing with whole numbers to look at a fraction and simplify it. But in any case, the goal of factorization is to take something that is complicated and rewrite it as the product of simpler things. And that's the same idea here with LU factorization. Our goal with LU factorization is to rewrite a square matrix A as the product of two matrices, L and U, where L is a lower triangular matrix and U is an upper triangular matrix. Right? Once again, the idea here is that triangular matrices are easier to work with than matrices in general. So if we can rewrite it in this way, we will have some things that we can work with a little bit more readily. And that's the advantage that we have here. Right. We have enough abstract videos that go through proof. So I don't want to spend time on the proofs here. If you're interested, our book goes through and walks through why this method works and when you will know that a matrix can be factored in this way. I'm going to take it just a couple of simple things. First of all, whenever matrix A is an invertible matrix, LU factorization is possible. There are actually more matrices that can be factored this way that are not invertible. If you go through some extension, we can actually even extend this and say that a matrix which is not a square matrix can be factored this way. But when you can factor a matrix, when you're able to work with it, it opens up several possibilities. Again, triangular matrices are easier to work with. If we're trying to solve a system of equations and the system is represented by a triangular matrix, the process of solving the system is significantly easier than the process for a matrix in general. If we're doing squares and other powers on matrices, that works out very nicely when we're taking powers on upper triangular matrices. It works out really nicely when we're taking powers on lower triangular matrices. And a couple of other things that are going to come up a little bit later in the course. where it just keeps coming up as this is something that will make our lives a little bit easier. Having said that, I need to readily admit that for the applications that we're going to be looking at in this course, actually performing the LU factorization is almost always more trouble than it's worth. Um, we're going to go through solving some systems of equations, and I'm going to specify that I want you to solve it using the LU factorization method, which is never something I would ever consider doing by hand, at least in the case where you have a single, um, where you have a single system of equations to work with. If you have multiple systems of equations, this might be nice kind of as a way stop in the finding an inverse of a matrix sense. But in general, it doesn't really save us all that much. So before I even get into anything else, I want to talk a little bit about the way that this is used, which very specifically is in computer programming. Some of you taking this course are going on to study computer science. And if you're going on to study computer science, chances are very good that you're going to spend some time working in numerical analysis, either in the academic study of numerical analysis or as a job doing data analysis. If you are not going into computer science, chances are very good that you're going into a number and computation heavy discipline: physics, engineering, economics, finance. And in those fields, you're going to be spending a lot of time taking information, rewriting it in a form that makes sense in linear algebra, and putting it into the computer software that handles solving systems of equations and handles doing linear algebra for you. LU factorization in a lot of setups, in a lot of types of matrices, and a lot of computer modeling is an efficient tool for letting the computer read and write the data in the matrix relatively quickly. So that's the reason that thinking about LU factorization is valuable. And with that in mind, let me get my head out of the way and let's look at a particular example. Oops. Right. So the process that we're going to use for LU factorization is Gaussian elimination, right? Gaussian elimination, not Gauss-Jordan elimination. And our goal is row echelon form, not reduced row echelon form. And very specifically, we're going to use only the operation that allows us to add a multiple of one row to another row. We are not allowed to multiply a row by a constant, so we're probably not going to end up with ones in the lead entries of each row. We're not allowed to swap rows, which could lead to something bad happening, and we'll see what that looks like a little bit later. But if it works out nicely, then this is going to be what we're looking at. And one more thing, instead of adding a multiple of one row to another, we're going to insist that we subtract one row from another, and we're going to keep track of our coefficients as we go through. All right. And this one kind of breaks down for smaller matrices. It feels like you're not doing much. So as an example, I'm going to take a look at a 4x4 matrix. 3, 1, 3, -4, 6, 4, 8, -10, 3, 5, 6, -1, and -9, 5, 2, 8. All right. I'm just going to perform elementary row operations, specifically the subtract, on this matrix. I'm going to take my first entry in the first row, first column, which is a 3. And I'm going to insist that everything below that 3 must become 0. So row 2 minus 2 times row 1, because 6 minus 2 times 3 is 0. Row 3 minus row 1, 3 minus 3 is 0. And then I have a negative 9. So I have to add 3 times 3, which is the same thing as row 4 minus negative 3 times row 1, right? And again, yes, I am going to insist that we write all of these as subtraction, and you'll see why at the end of the process. All right, but doing those operations, the first row stays the same. 3, 1, 3, negative 4. The second row, 6 minus 2 times 3, 6 minus 6 is 0. 4 minus 2 times 1, 4 minus 2 is 2. 8 minus 2 times 3, 8 minus 6 is 2. Negative 10 minus 2 times negative 4. Negative 10 minus negative 8, negative 10 plus 8, negative 2. Third row, 3 minus 3 is 0. 5 minus 1 is 4. 6 minus 3 is 3. Negative 1 minus negative 4 is negative 1 plus 4, which is positive 3. And then the fourth row, right? Subtract after multiplying by negative 3, or just multiply by 3 and then add. Negative 9 plus 3 times 3, negative 9 plus 9 is 0. 5 plus 1 times 3 is 8. 2 plus 3 times 3, 2 plus 9 is 11. And 8 plus 3 times negative 4. So 8 and negative 12 is negative 4. All right, that gets my first column looking nice. Then I go to the second row. Second row, second column is a 2. I'm not worried about what's above the 2 because I'm going for row echelon form, not reduced row echelon form. And I'm going to just do the subtraction down the rest of that row. So we're going to have row 3 minus 2 times row 2, it looks like, and row 4 minus 4 times row 2. All right, first row doesn't change. Second row does not change. Third row, 0 minus 0 is 0. 4 minus 4 is 0. 3 minus 4 is negative 1. 3 plus 4 is 7. Third row, 0 minus 0 is 0. 8 minus 8 is 0. 11 minus 8 is 3. Negative 4 plus 8 is positive 4. All right, my first column looks good. My second column looks good. On to the third column. I've got a negative 1 here. And let's clear out and make zeros the rest of the way down, which in this case is fairly straightforward. I'm going to take row 4, and it looks like I'm going to subtract negative 3 times row 3, right? Just add negative 3 plus 3 times negative 1. I'm sorry, 3 plus 3 times negative 1 is 3 minus 3, which is 0, but I have to write it as subtraction, minus negative 3. All right, so the first row, the second row, the third row, all stay the same. And then the last row, 3 plus negative 3 is 0. 4 plus 21 is 25. And whenever we take the time to put a, whenever we take the time to put a matrix in row echelon form, the resulting matrix is always an upper triangular matrix. And in fact, that is going to be the upper triangular matrix that I care about. And then I kept saying every step along the way that I had to insist that we set these all up as subtraction. And that's for this last step. My lower triangular matrix, all right, in order for multiplication to actually work, it's going to be a 4 by 4 matrix. The main diagonal of the lower triangular matrix is going to be all ones. Everything above the main diagonal is zeros. That's what it means to be a lower triangular matrix. And then the other entries are those numbers I circled, the coefficients from the elementary row operations. The first step, I subtracted 2, I subtracted 1, I subtracted -3. The second step, I subtracted 2 and 4. The third step, I subtracted -3. And there's my lower triangular matrix. It is not immediately apparent, it shouldn't be immediately apparent, that this actually works. And again, if anyone is really interested in the why and how this works, I invite you to read through the proof in the textbook. I don't want to spend the time going through that in detail. So instead of trying to do that, I want to prove that this works by checking it. Right? We can verify that this works by multiplying L times U. All right, multiply first row, first column. 1 times 3 is 3, all the rest are zeros. First row, second column is going to give me a 1. First row, third column is going to give me a 3. First row, fourth column is going to give me a -4. Second row, calculations start to get a little bit messier. We've got 2 times 3, which is 6, 1 times 0, which is 0. We've got 2 times 1 and 1 times 2, all told that's 4. We've got 2 times 3 and 1 times 2. So that's 6 plus 2, which is 8. We've got 2 times -4, 1 times -2. All told, that's -10. Then we'll take our third row and multiply by each column. We've got 1 times 3 and a whole bunch of zeros. So that's going to be 3. 1 times 1, 2 times 2. 1 and 4 is 5. 1 times 3, 2 times 2, 1 times -1. So 3, 4, and -1 is 3 and 3, or 6. Then we've got -4. 2 times -2 is another -4, and 7. All right, so -8 plus 7, -1. And then my fourth row. -3 times 3 is 9. -3 times 1, 4 times 2, and then some zeros. -3 plus 8 is 5. Then we got -9, 8, +3. All told, that's going to be 2. I've got 12, -8, -21, 25. All right, 12, -8, -21, +25. I guess that's going to be 37 minus 29, which is 8. And if I scrolled the screen back up, that is in fact exactly the matrix A we started with. I didn't quite arrange this in a way that I can fit myself on the screen, so I apologize. I was going to jump in here, but my head will just be in the way. I mentioned that LU factorization was a nice tool because it allows us relatively easy storage of our results. And the reason is, if I know that this is an LU factorization, I don't care about these ones. I can fill those in later. I care about 2, 1, and -3. And I've got a couple of empty spaces here where there would be 0 otherwise. I can use that as a place to store things. All right. Following a computer program that does that is kind of messy, but that's the computer algorithm. Let's figure out what the coefficient is and put it in the first column, and then do the calculations down the rest of the row. Let's figure out what the coefficient is, do the calculations down the rest of the row, because I know that that first column is going to be all zeros. And then when I go to the next step, I know that that column is going to be all zeros. So I don't ever store the 1, I know it's going to be there. I store all of the other numbers, and that way I can use a single matrix, a single place where I am storing data, instead of having to go to 2 different places in memory. Right? If you are in computer science, if you're studying how programs work, hopefully you can start to see from there some optimization tools that you can use and why LU factorization is so valuable in computer science. If you're not studying computer science, again, all you really need to know is that this is a thing that we can do. It allows us to solve systems of equations, and computers are fairly happy to do it. So let's see. Come on, there we go. Let's see how that works. All right, so let's say that I have a system of equations given by this matrix A we've been dealing with. A column vector of variables, x1, x2, x3, x4. And on the right-hand side, some column vector that we are looking at. So in this case, just 3, 1, 2, 4, something relatively easy to work with. And I know that matrix A has an LU factorization. I just spent how much time finding it. So my first step is going to be to rewrite this using my LU factorization. So matrix L, 1, 0, 0, 0, 2, 1, 0, 0, 1, 2, 1, 0, -3, 4, -3, 1. Matrix U, I'm leaving a little bit of space so I can come back in here and jot some notes later. Matrix U, which is almost off the page, but we can still read that. 3, 1, 3, -4. 0, 2, 2, -2. 0, 0, -1, 7, and 0, 0, 0, 25. That's being multiplied by my unknowns matrix, x1, x2, x3, x4. And the result I get is the matrix 3, 1, 2, 4. All right. We did an LU factorization. I then factored the matrix. Now let's see if I can make sense of what I'm trying to do here. This is why I left a little bit of space, because I want to insert a couple of extra parentheses. If I go ahead and tried to do this calculation, if I knew what x1, x2, x3, and x4 were, that calculation would give me a vector out, right? Multiply a square matrix times a column vector, you get another column vector of the same dimension. I don't know what the result is going to be because I don't know what x1, x2, x3, and x4 are, but I know it's going to be a column vector. And since I'm a mathematician and mathematicians are boring, the next letter after x is y. Let's just call it a bunch of y's. y1, y2, y3, y4. And then I'm going to substitute in. The stuff in parentheses in that last equation is now this new column vector. So I have the lower triangular matrix 1, 0, 0, 0, 2, 1, 0, 0, 1, 2, 1, 0, -3, 4, -3, 1 times this new matrix y1, y2, y3, y4 is equal to 3, 1, 2, 4. And solving a system of equations when you have a triangular matrix is incredibly easy. We can just churn through. This is a lower triangular matrix, so we start at the top and work our way down. The first equation says that y1 equals 3. The second equation says that 2y1 plus y2 is equal to 1. But of course, I already know that y1 is 3. Extra pen mark for no good reason. I get that y2 is -5. The third row tells me that y1 plus 2y2 plus y3 is equal to 2. But I know that y1 is 3. I know that y2 is -5. Right? 2 times -5 is -10, plus 3 is -7, which means that y3 must be equal to 9. And then my last row, almost running out of room here. Actually, let's come way over here to finish this last row out. -3 times y1 plus 4 times y2 minus 3 times y3 plus y4. I will find more room. There we go. A little bit more room. That's equal to 4. And again, I know what y1, y2, and y3 are. So I can churn through that. -3 times 3 is -9, -20, -27. And that's a really hideous number, but we can work with it. Negative 29, negative 56. Not a good day to not have my calculator on me. All right, but y1, y2, y3, and y4 are all known. 3, negative 5, 9, 60. And that's not what we were trying to solve for, but it is a step along the right direction because now I can go to that white system of equations that we looked at before. And now that I know the values of y1, y2, y3, and y4, I can plug those in and I can use this system to solve for x. So we did the same thing you do when you factor a polynomial equation. We went from having a single equation that was complicated to having two equations, each of which are easier. But this is working with matrices, this is linear algebra, and that means that everything we do just takes a ton of writing. There's no getting around it. This time we have a system of equations with an upper triangular matrix. And we can solve a system with an upper triangular matrix by starting at the bottom and working our way up. 25 times x4 is equal to 60. So divide both sides of the equation by 60. 25 or 60 over 25 reduces to 12 over 5, which I guess is 2.4 as a decimal number. And then we go to x3. Minus x3 plus 7x4 is equal to 9. If we just take that third row and multiply it through. Right? 7 times 2.4 is 16.8. And 9 minus 16.8 is negative 8.2. And now I know what x3 is. Making my way up to the next line. Second row, if I multiply that out, I would get 2x2 plus 2x3 minus 2x4 is equal to negative 5. I don't know what x2 is, but I know that x3 is 8.2, and I know that x4 is 2.4. Right, 16.4 minus 4.8 is 11.6. Negative 5 minus 11.6 is negative 16.6, and divide by 2, x2 must be negative 8.3. I'm running out of room here once again because it's linear algebra and it just takes that much space. But I've got 3 times x1, which I don't know the value of, plus 1 times x2, which is negative 8.3, plus 3 times x3, which is 8.2, minus 4 times x4, which is 2.4. Right? The first row of this system tells me that that should give me 3. And when I multiply this out, all right, 24.6 minus 9.6 is 15.0. Subtract a further 8.3, and you're going to get 6.7. Right? X1 is going to be negative 1.233, etc. Again, I know it is large. It takes a lot of writing to get through these problems. But the whole idea of this whole process, the whole idea of LU factorization, and honestly, the idea of linear algebra in general, is to take something that looks complicated and find a way to turn it simple so that each step along the way is trivially easy. Right? We had to do almost nothing as far as algebra goes. Once we were able to get through and find the LU factorization, the rest of it was smooth sailing. We had to um, do some addition and subtraction to get the LU factorization. From there, we had to solve a couple of linear equations. I mean, 8 of them all told, but they were all easy to solve. Right? So that's where the LU factorization becomes useful. It takes a lot more work to get the LU factorization in the first place, but it turns your system into a system with twice as many equations, most of which are incredibly easy to solve, so you save yourself a lot of computational complexity on that end. All right, let's wrap up with one for you to try. I'm going to give you negative 2, 1, 2, 5 times x is equal to 5, 1. All right, this is a system of 2 equations in 2 unknowns. You could have solved this system before you even came into this course. It is something that you've been seeing for quite some time. But specifically, I want you to use this as a tool for practicing LU factorization. I want you to factor this matrix into a lower and upper triangular matrix. And then once you have done that, I want you to use those 2 matrices to solve this system of equations. It is going to be harder than if you had just used the tools that you learned in a basic algebra course. But that's what makes it good practice. All right, take a few minutes, see what you can do with that, and I'll see you in the next video.